everyone. I'm Gijun Nam from IBM Research, but I'm also a president-elect of CEDA. So I'd like to welcome everyone to this IEEE CEDA distinguished speaker luncheon talk featuring Dr. Suze King Liu today. Before we get into the main event, I hope everyone here and your family is well and safe. Also, I really appreciate your efforts to attend this conference, DAC, and this event in person. I don't know, maybe it has been more than 2 years, and now a virtual conference became sort of the norm, but at the same time, kudos to this DAC, EC, and management to have a real conference here. Certainly, it is great to meet you all in person today. So since this is CEDA sponsored event, I'm obligated to go over a little bit about CEDA introductory material. So I'll promise that I'll make it very short. Please bear with me a few more minutes here. So what is CEDA? CEDA stands for Council on Electronic Design Automation. It is a council formed around 7 member societies: APS, Antennas and Propagation, CAS, Circuits and Systems, Computer Society, Electronic Devices Society, MTTS, Microwave Theory and Technique Society, and of course, SSCS, Solid State Circuit Society, and Electronics Packaging Society. So vision is pretty straightforward. Our vision is to become the leading provider in IEEE of the technical information and community services in design and design automation of electronics as well as the embedded system. So what kind of technical information and services are we talking about? First one is CEDA-sponsored publication. We are sole financial sponsor of the premier IEEE transactions on computer-aided design of integrated circuits and systems. Also, we are sponsoring Design and Test Magazine, Embedded System Letters, and most recently JX-CDC, a journal on exploratory solid-state computational devices and circuits. Also, CEDA actively recognizes the scientific activities of the members of the CEDA community by sponsoring or co-sponsoring numerous awards in the field. For example, Phil Kaufman Award, Richard Newton Technical Impact Award, Ernest Koo Early Career Award, and of course IEEE Fellowship. These are more like awards related to your career. Also, we sponsor the Best Paper Award awards like TCAT Donald Patterson Best Paper Award and ICCAT William McCullough Best Paper Award as well. And also we are sponsoring various services awards like Distinguished Services and Outstanding Services. And most recently, we initiated new CEDA award for sponsoring or supporting participation in IEEE Women in Engineering area too. What kind of services and activities are we engaged? Distinguished Lecturer Program is one of the biggest activity here. As a matter of fact, this luncheon talk is part of this program at DAC. Also, we are hosting similar Distinguished Lecturer luncheon talks in our sister conferences like DATE, ICCAT, and ES Week. Distinguished lecturer visits we are supporting to anywhere in the world, although because of the pandemic situation, it became sort of more like a virtual events in the recent years. Also, we are supporting various EDA-related conferences and workshop activities. One of the most famous one is this CAD contest. And CEDA is willing to support any EDA-related activities with a high emphasis on involving students and EDA professional. So As you can see over here, the limit is only your imagination. So feel free to let us know by using these various forms of social medias, also to stay up to date on all CEDA news and events here. I just skipped the one slide over here, but CEDA local chapters worldwide, this is another very important activities that we are participating to establish local chapters globally, also nurture more meaningful technical activities to provide a service in a local community. So with that, without further ado, let me introduce today's distinguished speaker, Dr. Suje King Liu. Dr. Liu earned her BS, MS, and PhD degrees in electrical engineering at Stanford University, and she was a member of research staff at the Xerox Palo Alto Research Center. In 1996, she joined the faculty of the Department of EECS at the University of California, Berkeley, where she is now Dean of the College of Engineering. Dr. Liu is internationally known in academia and industry for her innovations in semiconductor devices and technology, and is highly regarded for her achievements as an instructor, mentor, and administrator. She is a fellow of the IEEE, an elected member of the U.S. National Academy of Engineering, a fellow of the U.S. National Academy of Inventors, and a board member for Intel Corporation and for MaxLinear. She has numerous awards and honors, which I cannot go over all of them because of the lack of time, but without further ado, please welcome Dr. Liu to the stage.
Thank you so much for that very kind introduction, and good evening, or no, good morning, everyone. It's really nice to see people in person. I think I can take my mask off, but you cannot. Sorry about that. Okay. All right, so it's really my pleasure to speak to you before your luncheon today to share with you my perspective on emerging chip technologies for the age of ambient intelligence. Now, so usually I start out a little slow, so warm people up. Shown here is a vision of the age of ambient intelligence. As we all know, advancements in information and communication technologies have given rise to cloud computing and the Internet of Things, which together with advancements in AI and machine learning are giving rise to artificially intelligent systems for managing, for example, critical infrastructure for smart cities, managing personalized healthcare and medicine for smart hospitals, automating vehicles and optimizing traffic flow for smart highways, and optimizing factories and logistics for smart factories. Now, artificially intelligent systems require real-time processing of large quantities of data, and this is possible today because the capabilities of computing devices have improved dramatically at an exponential pace over the past 120 years and are rapidly approaching the capability of the brain. Now, Kurzweil's law states that the performance of the most advanced computing device measured in number of calculations per second per dollar increases exponentially in time. And this is because technological innovation itself is accelerated by advances in information technology. And we all know that the integrated circuit technology and industry has provided the exponential pace of improvement in computing technology over the past 50 years. So underlying Kurzweil's law is Moore's law, which states that the number of transistors on the most advanced microprocessor chip doubles every 2 years. And we can see that Moore's law is alive and well. Steady advancement in chip manufacturing technology over the past 50 years has enabled ever smaller transistors to be manufactured so that we can interconnect them together on a single chip, more of them, for greater functionality of a chip and at lower cost per function. And this has enabled new electronics products with greater information processing capability, resulting in market growth. And semiconductors invest continually a portion of their profits into advancing the technology. So this virtuous cycle has gone on for over 50 years. And today's most advanced microprocessor chips, you probably all know, have over 40 billion transistors. Now, underlying Moore's law are advancements in transistor materials, processes, and structures that have enabled transistors to be miniaturized to below 20 nanometer minimum feature size today. Now, in the 2000s, Intel was the first to incorporate silicon germanium in the source and drain regions to induce mechanical strain, to enhance hole mobility, to allow transistors to conduct more current, so the circuits can operate more quickly. They also introduced high permittivity metal gate electrode stacks to improve capacitive coupling between the gate and the channel, again to improve performance. And eventually in the 2010s, Intel was the first to introduce advanced transistor structures like the FinFET, and other companies like Global Foundries and other companies introduced thin body transistors that are planar for fully depleted SOI. So these advances in materials and structures enabled transistors to be miniaturized, controlling off-state leakage pretty well, and enhancing on-state current, allowing voltage scaling, a little bit of voltage scaling as well. So today, I think people are anticipating within the next 3 to 4 years that another change in transistor structure will occur. Rather than wrapping the gate around 3 sides of the silicon fin to improve gate control, we would like to wrap it around all 4 sides. So the nanowires that are stacked on top of each other to have good layout area efficiency are likely going to be introduced in high volume production within the next 5 years. And we generally, for good layout area efficiency, we expect nanosheet transistors. So the widths are wider for each of the nanowires to provide for more current flow per unit area. Okay, so, but at the same time that transistors have been advanced, other things have been added to chips. So transistors, as you all know, are primarily in digital computing chips, are used as on-off switches to charge or discharge voltages in a circuit. But modern electronic devices have functionality much greater than just computing. So smartphones, for example, have functionality including wireless communication, various sensing capabilities for sound, motion, and light. And these capabilities have been made possible because of advancements in manufacturing technology to incorporate thin film resonators, microelectromechanical devices, and photonic devices. But yet, looking forward, there are still many technological challenges that must be overcome in order for ambient intelligence to become a reality. And these, to the university researchers like myself and many people here, present opportunities. So I'll just mention a few. First of all, there's a looming power crisis because fundamentally modern transistors have a fundamental limit in how steeply they can turn on and off as you change the gate voltage. And this limits the voltage scaling, and then this leads to power density increases. So this is a fundamental issue for conventional CMOS technology. So we need alternative switch designs. For the Internet of Things, the number of devices, computing devices in the world is projected to continue to grow exponentially. So they will far exceed the number of people in the world. So a lot of the computing devices will probably be embedded in our environment, in things in the environment, in us or on us. And so more flexible form factors and compact form factors will be needed to realize that vision of ubiquitous computing. And these devices probably need to have integrated energy generation, scavenging from the environment, and also energy storage. And then finally, the big data with self-driving cars and so on and so forth, there's going to be a continued proliferation of big data or large data sets. And so we need to develop like a more inexpensive, lower power storage technology. And I just wanted to mention today a few examples of research that is going on at UC Berkeley to address those challenges and opportunities. And so I just wanted to acknowledge somebody previously mentioned that they are very familiar with the Berkeley Sensor and Actuator Center. The Berkeley Emerging Technologies Research Center is a relatively new center at Berkeley. It came out of an NSF Science and Technology Center on energy efficient electronic science. But today we have about 10 faculty that represent physics, chemistry, material science, electrical engineering, and that spans devices, circuits, and architecture, working together to really address those challenges that I listed on the previous slide. And one of the things that we have done well at Berkeley is collaborate with industry to not only guide the research, but also to transfer the results of our research more quickly so that they can benefit the industry. So the Better Center is actually an industrial consortium where companies meet with the faculty and the students at least twice a year to learn about the research, provide feedback, and students, go on to work for these companies, and the companies have early access to the students as well as our research results. I just wanted to acknowledge these companies that are presently members of the Better Center. I'd like to welcome any additional companies that are interested to join us. One thing I'll touch upon at the end of my talk is the semiconductor innovation ecosystem. So you notice that the companies here, let's say for example Meta, they're not traditionally semiconductor device technology like companies, right? But it's really important to bring together people from across the semiconductor ecosystem, from the materials to equipment to the fabs to the chip designers and to the customers for semiconductor chips, to come together, talk about challenges, and to work together towards solutions. So in the Better Center, we have a few thrusts to address those challenges I mentioned earlier. And so for the rest of the time today, I'd just like to touch upon just a few of those thrusts to give you an example of things that we are working on that can overcome the fundamental limits of CMOS technology today. So one thrust is next generation switches. As I mentioned, transistors have fundamental low voltage requirements, switching voltage requirements. So we've been looking at switches that are more sensitive to a control signal, and that includes mechanical switches, which is what I'm going to talk about today because that's in my research group. But these faculty members listed here are looking at various approaches. And a lot of this is enabled because in the EDA industry, we've developed modeling capability, technology, computer-aided design tools to help us explore new device concepts even before we can fabricate them and validate the concepts in the lab. So I'll talk a little bit later in detail, show you some results from mechanical switches. But years ago, when I was talking with some circuit design colleagues, they basically told the semiconductor device researchers, all we want is our switches that have zero leakage, right? Because they were really, struggling to deal with transistor leakage. And not only that, but variability in the manufacturing process. The threshold voltage for each transistor can vary quite a bit. So that leads to large variations in the leakage current and also the on-state drive current, and therefore the circuit performance. So for that reason, over 10 years ago, my group started to look at mechanical switches. So if you remember from the Kurzweil's law plot, mechanical switches were used for computing like a century ago, right? So we're going back in time to revisit mechanical switches. So the nice thing is that a mechanical switch has zero leakage because there's a physical air gap between the conductive electrodes, the source and the drain. And you can operate a mechanical switch just like a transistor. You apply a voltage to a control electrode called the gate, and the electric field induced between the gate and the source induces an electrostatic force. And the larger the actuation area, the larger that force. So the lower the voltage you can apply, or the smaller the air gap, the actuation gap, the higher electric field and the less voltage you need to use. So electrostatic force is used to physically actuate a movable electrode into physical contact with the conducting electrode. So the source and drain come into contact, current can suddenly start to flow. It's essentially a zero subthreshold swing, and the current here is limited artificially. We just didn't want to weld the contact here. But this is a typical measured transfer characteristic where you have immeasurably low off-state leakage current, and suddenly the switch turns on when physical contact is made. Now, when the switch is on, there's adhesive force, and so when you lower the voltage back down, the spring restoring force of the beam actuates the source out of contact, but there's going to be some hysteresis because of that adhesive force. So over the years, we've learned how to engineer the contact adhesive force to minimize that hysteresis voltage. And so in principle, a mechanical switch can operate with just that hysteresis voltage as the gate voltage swing. So you have zero static power consumption and very, very low active dynamic power consumption. Now, for logic applications, three-terminal switch is not as useful because if you rely on the gate-to-source voltage difference to turn on the switch, well, that means that the state of the switch is dependent on the source voltage, and that's not ideal. We'd like to have the switching voltage, the gate switching voltage, to be constant no matter what the voltage on the source is. So my group has developed a long time ago a four-terminal relay design where you have a fourth terminal called the body, and as the voltage between the gate and the body, that induces electrostatic force that turns on the switch. And the voltage on the source and drain can be quite different from the voltage on the gate and the body. So this device can operate very well passing low or high voltage or any kind of voltage. So it can be used as a pull-up or pull-down switch. Another nice thing about a mechanical switch is that electrostatic force is ambipolar. So it doesn't matter if the gate voltage is higher or lower than the body voltage. It just needs to be different enough to induce the electrostatic force needed to turn it on. Now, in the lab at Berkeley, we fabricated a lot of micron scale mechanical switches. This is a scanning electron micrograph view of one relay. The body is this movable plate in the center, and it's suspended at its four corners by folded flexures. And you can see the anchors. There are 4 anchors at the corners of this layout. So the body actually moves out of plane of the silicon wafer up and down, and it's suspended over the gate electrode. So there's electrostatic force that moves it up and down. And there's a source electrode, if you see on the right, there's a source electrode that is routed underneath the movable body electrode that is the one that actuates into and out of physical contact. Now, there's no current that flows to the body because it's electrically isolated from that source electrode by this aluminum oxide insulating layer. So there's no gate current, no DC gate current or body current. Only the current that flows is between the source and drain electrode in the on state. Okay, so if we just want to create logic circuits with mechanical switches, what we can do is we can apply a body voltage to actuate the structure close to contact and rely on a very small gate voltage to turn on the relay. And the gate voltage swing just needs to be greater than the hysteresis voltage. And so at Berkeley, we've been able to demonstrate mechanical logic circuits operating with VDD, supply voltage down to actually 10 millivolts. We haven't published that yet. But easily 50 millivolts, it's no problem turning a switch on and off reliably. And so shown here on the right are the waveforms on the top, the input waveforms for a 2-to-1 multiplexer, and then the controls, the select signal is the third row, and then the output is shown in the bottom waveform. So it just shows proper operation of a 2-to-1 multiplexer that requires only 2 relays. So yes, relays can be larger than a transistor, but you can perform functions more efficiently, right, with fewer switches if you use these 4-terminal relays. So this is just one example. If you really care most about energy consumption, like for Internet of Things applications, then mechanical switches could actually be very interesting. Now, other types of very sensitive switches include graphene nanoribbon transistors. Now, graphene, the band gap, the energy band gap of graphene depends very sensitively on the width of the graphene nanoribbon. And so my colleague, Professor Boker and Jablanovic at Berkeley, they have collaborated with people in chemistry to find ways to chemically synthesize graphene nanoribbons precisely, so they can control within less than 1 angstrom, an order of an angstrom, the width of a graphene nanoribbon. And they've been able to achieve working transistors with a sub-1 nanometer wide graphene nanoribbons. And because the surface area to volume ratio of a graphene nanoribbon semiconductor is very high, these can be very useful as sensors, right? Very sensitive switches. Now, for memory, my colleagues are looking at ferroelectric and magnetic materials. And let me just talk a little bit about this. So just a couple of examples here. So we would like to have embedded non-volatile memory devices integrated for very ultra energy efficient mobile computing and Internet of Things devices. So the Boker and Salahuddin groups are developing current-driven magnetic devices. So rather than using a magnet to switch the magnetization of a nanoscale magnetic material, we can use current to actually flip the magnetization. So the interesting thing of the upper plot is this waveform, it's this green pulse. So we've shown that a nanomagnet can switch within 6 picoseconds the magnetization with a pulse of electrical current. So this just shows that nanomagnetic devices can actually switch pretty quickly and be scaled to very small dimensions. The image on the lower part of this slide is from Professor Salahuddin's group, who made the groundbreaking discovery that spin-orbit torque can be observed at room temperature using fairly common materials. So he uses iron silicide and cobalt. There's a bilayer shown here. So this basically opens the pathway for implementing new memory technologies using fairly common materials that are already used in CMOS processes today. All right, now, if we want to communicate signals across a chip, it's more energy efficient if we use it with photons rather than charging and discharging long interconnect lines. So people have been looking at optical interconnects on a chip. Not only, today optical signals are used to route signals from server to server, rack to rack in a data center. Now, one of the challenges for photonics on a chip is that the light emitting devices and the light detecting devices have to be miniaturized, right? They have to be small. But the wavelength of light is kind of long compared to the transistors today. So this is a fundamental challenge. For the sake of time, I'll just point to the example on the bottom here. So Professor Ali Javi at Berkeley, his group came up with a novel way to create a light-emitting device. So for those of you who might be familiar with semiconductors, if you have a metal in contact with a semiconductor, it forms a potential barrier called the Schottky barrier. So that usually prevents electrons and holes from going into and out of the semiconductor. But what he's found is that by applying an AC signal, so positive and negative voltage at a reasonable frequency, what they can do is make that barrier so narrow that carriers can tunnel through. So you can, in one phase of the voltage, you inject electrons into the semiconductor, and in the next phase, you inject holes into the semiconductor. And you have electrons and holes, and they recombine. And of course, if it's a direct bandgap material, you can emit light. So it turns out that his group has shown that this novel design, very simple if you think about the circuit, can emit, you can change the semiconductor material, and you can emit light in a broad range of wavelengths by tuning the semiconductor material. And it spans from ultraviolet down to, ultraviolet to UV wavelengths. So, and these can be miniaturized. And another novel aspect of this work is that he uses a carbon nanotube array that's porous to help facilitate the fabrication of these devices. So this is just an example of some innovations in photonics that will help to lower the energy consumption of chips in the future. Now, finally, talking about Internet of Things applications, well, we'd like to have some flexible electronic systems that have computing and memory on them, but this requires high-quality semiconductor materials, and that's a fundamental challenge. We have to develop new tools, new processes, maybe new materials to address that challenge. So shown here on the top is an example. Again, Professor Ali Jabi, he's come up with a templated liquid phase growth of compound semiconductor materials so you can grow these materials from liquid phase at about 200 degrees Celsius, which is compatible with some reasonably low-cost plastic substrates. And so they've gotten single crystal, nanoscale semiconductor materials grown successfully on polyimide that's flexible here. Now, another colleague, Professor Arias, is on the bottom here. Her group has developed a variety of sensor devices that can be fabricated on plastic substrates using roll-to-roll printing. So rather than moving wafers in and out of tools, roll-to-roll processing, printing, and so on and so forth is lower cost per unit area. So they've actually leveraged the phenomenon of potentiometric mechanotransduction. So they've developed stretchable mechanical sensors that can have higher pixel density, so sensing resolution, and data acquisition speed. And this technology on the lower right is implemented with all solution processing, so they can just print or do roll-to-roll processing for ultra-low cost. Okay, and the final category I'd like to highlight is system integration. So future information and communication systems provide the context for research that is conducted in the Better Center. We collaborate across physical electronics to IC design to co-optimize new devices with new computing architectures. And so I'd like to tell you now, coming back to mechanical switches, ordinarily a semiconductor device researcher is not going to look at mechanical devices because they're bigger and they're slower than transistors. But I'll give you some examples of why they're actually intriguing. So of course, Moore's law is all about increasing functionality for relatively minimal increase in cost per function. And so over the years, the semiconductor industry has not only made advancements in materials and structures for transistors, but also for the back end of line metal layers that are used to interconnect those billions of transistors together. So if you look closely at the cross-section of an advanced CMOS chip today, you'll see that some of them actually have air gaps in between the wiring in some layers. And this is because as you pack transistors more closely together, the wires have to be more densely laid out, and you don't want to have too much capacitive coupling between those wires, capacitive load, right, because that slows down the circuit. And so air has lower permittivity than the dielectric, and this is why the industry has developed the ability to form air gaps between metal wires. Now recall that a mechanical switch only requires conductive electrodes, and some of them should be movable, right? So we can leverage the advancements that the semiconductor industry has made for the back end of line technology to implement mechanical switches with relatively low incremental process cost. Now, mechanical switches being slower than CMOS transistors, we really don't want to replace every single transistor with a mechanical switch. We would like to use them in a complementary fashion. So we can think of a mechanical switch implemented in back end of line layers as a reconfigurable interconnect, for example, right? Because the way that the transistors are interconnected determines the functionality of the chip. And so if we can change the physical configuration of the interconnects, that means we can reconfigure the operation of the chip. Now, shown here is just a simulation of a mechanical switch implemented with multiple layers of metal in the back end of line, and also with some of the vias in between those metal layers. So the movable electrode comprises vias and metals patterned all to line up like this. And we have patterned electrodes on the left and the right side to actuate the electrode either to the right or to the left. But physical contact, and therefore current flow, only occurs in the uppermost metal layer between the movable beam and one of the data electrodes. Now imagine that you have a 2D array of these reconfigurable switches, and the data electrodes can be running all along the one direction in the array, as well as the actuation electrodes, and the bit line at the bottom there runs in an orthogonal direction. This switch has a much smaller footprint than the switch I showed you earlier, and because it's vertically oriented, and you can easily integrate a diode at the bottom of the switch to force current to flow only one way through that movable electrode. So how do we fabricate this? Well, my student has just used a standard PDK. We've done this in 65 nanometer CMOS technology, and then more recently in 16 nanometer CMOS technology. What she does is she patterns the upper layers of metal to serve as a mask for anisotropic etching away of the dielectric that's surrounding that movable electrode. So after we receive the chips back from the foundry, we process them in our nanolab to do a dry etch. It's actually a multi-step etch to release that beam so it can move back and forth. And here's the initial experimental results. Plan view SEMs on the left, showing the as fabricated switch, back end of line, single pole double throw switch, and then after it's actuated to be in contact with a data zero conductive electrode. And then shown on the right is the cross-sectional SEM showing multiple layers of metal patterned to form the movable beam. You have the actuation electrodes on the lower layers, and then the contact conductive electrodes in the upper layer. Now, the benefit of transistor scaling or CMOS technology scaling is that you bring metal pitches down over with each new generation. So the closer or the smaller the air gap, the more electrostatic force that you induce when you apply a voltage. So this allows you to lower the actuation voltage of these mechanical switches. And so the plot in the middle here just shows measured switching voltage versus simulated switching voltage to verify that indeed the operating voltage of our mechanical switches is scaling as we expect. And we project that by the 7 nanometer technology node, the metal pitches and the air gaps will be so small that the voltages needed to actuate these switches will be perfectly compatible with CMOS transistors. Okay, so what is a more interesting use of these mechanical switches? Well, what we've demonstrated, this is in 16 nanometer generation technology, I believe, is an integrated circuit that has an array, 4 by 2 array of mechanical switches that I showed previously. And they're each programmed to touch either a data 0 or a data 1 line. And they're programmed such that the data lines that are, the bit lines that are running horizontally, only the bit line that is, that has switches with the information stored corresponding to like certain input string, only one bit line will actually be pulled low. Okay, so in this particular example here, the switches in the first row, which corresponds to data input string of 0, 0, they're each programmed to touch the data 0 line. Okay, and if you look closely, let's say the second row, it corresponds to input string of 1, 0. So the switches are set to store, 1, 0. So it just turns out when you apply the voltages to the input lines, only one of those horizontal bit lines is actually pulled low. So you can think of this as a decoder circuit. And the measured waveforms on the right show that this works properly. And you can reprogram the switches, so you can actually update the functionality of this circuit over time. Now, a lookup table is one way to perform a computation. You look up the answer rather than computing it if you can have a large enough memory array. And so simply by adding an output string section to that previous decoder circuit, remember that's designed to allow only one bit line to be pulled low. Well, we can isolate the output portion from the input portion with a gated CMOS buffers, shown here with the blocks, so that we can pre-charge the output lines all high. And then once we input the address on the left side, only one of those bit lines will be pulled low. Then we can use the gated CMOS buffer to drive one line low and discharge the output lines to read out the information. So this is a demonstration of a CMOS plus NEMS lookup table that is much more compact than the CMOS implementation, which requires that you store the answers in non-volatile memory and then load them onto SRAM, CMOS-based SRAM, and then you do the address and you read out the answer. Here it's just all reconfigurable interconnects on top of CMOS, much more compact, and from simulations, it's also much more energy efficient and time is faster by orders of magnitude compared with a CMOS implementation. Okay, so that's just to show you that if we want to innovate in new devices, we really need to work together with circuit designers, chip designers, because otherwise we're just going to simply work on making smaller transistors and switches, right? And that might not actually yield exponentially better results as what I showed here. Now, taking it a bit further, what if we want to look at completely different computing paradigms? Now, information today is stored in ones and zeros, charged versus discharged nodes in an integrated circuit. Well, another way you can encode information is by phase. So if you have an oscillating signal, it can either be in phase or out of phase, or it can take on one of two phases, 0 and 180 degrees. And that can be used to encode bit 0 and bit 1. And this was proposed by other researchers, including these researchers, Professor Jajit Roy-Chaudhuri, who's in, I think, your field of expertise at Berkeley. Okay, so key here is that you apply a oscillating signal, what we call the subharmonic injection locking signal, SHIL, I'll call it for short. That's the yellow signal here. It's oscillating, it's the blue signal that's oscillating at a frequency that's roughly twice the oscillator, the yellow oscillator frequency. So it just turns out that if you inject that SHIL signal, any oscillator will sort of lock into phase, and it can lock into one of two phases, as shown on the left and the right here. Okay, so the idea here, the reason why this is interesting is because oscillators can be used to implement a type of computing architecture called the Issing Machine or Issing Machine. So imagine you have a network of interconnected oscillators, and they can either be have phase 0 or phase 180 degrees from each other. And each of these oscillators, the minimum energy configuration will depend on how those oscillators are interconnected with each other. So it turns out that so this is what I'm going to show you experimental results for next. So we can inject this SHIL perturbation signal into each of these oscillators, and each of them will lock into phase, and it'll be one of two phases, okay? And the minimum energy configuration will, as I said, depends on how the strength of their the coupling. And it turns out that these machines are potentially very good for solving combinatorial optimization problems. So I picked an example that hopefully you can relate to. In VLSI design, let's say you have blocks of circuitry, let's say n blocks of circuitry, 4 shown here, and the problem is to minimize the chip area by placing those blocks optimally on to minimize the W times H. It turns out that this floor planning problem can be mapped onto an Issing machine with this number of spins, 3 times n cubed spins. Okay, so it's quite interesting to consider a different way to solve these combinatorial logic optimization problems, which my understanding is that is quite common in the field of machine learning. Okay, so the key here is that mechanical switches also can be used as oscillators. And let me explain how this is done. Again, I'll show here in the schematic on the left, a 4-terminal relay. Let's say we apply a gate-to-body voltage that's not quite enough to turn on the relay. So remember, the source and drain electrodes are opposing each other. So there is a little bit of electrostatic force between the source and drain electrodes if they're separated because there's some actuation area there. So let's say we barely do not turn on the relay, but then we apply a voltage to the drain. And that drain to source voltage difference is enough to induce electrostatic force to turn on the relay. Now when the relay turns on, current conducts, and that causes the voltage on the drain to drop. And then that eliminates the electrostatic force. So then the relay will turn off. But then when the relay turns off, the drain voltage charges back up and induces electrostatic force to turn the relay back on. So in this way, by applying DC voltages, you can get a relay to self-oscillate. What will be presented next week at the International Electron Devices meeting are some experimental results. I'll just show some glimpses here. This is a measured voltage versus time, showing if we ramp up the drain voltage, the blue curve, we start to see the voltage on the drain oscillate. And for the large relays I showed earlier, the natural resonant frequency is around 1 megahertz. So it's oscillating close to a megahertz. Now we can inject that shill perturbation signal to like the body electrode, like this. And when we do so, what we find is that if you look at the drain voltage, that oscillatory signal, and compare it with the shill signal, we see that the frequency, it basically locks in within a few tens of cycles. So of course we can design these switches, these mechanical resonators. The smaller they are, the higher the oscillating frequency, so they easily can achieve gigahertz frequencies. So within dozen cycles of oscillations, you achieve the answer, right? So you can solve a combinatorial optimization problem more quickly, and ideally if you design the oscillators properly with lower energy as well. Okay, so those are just examples of innovations that people are working on to really address the challenges that I mentioned earlier, largely energy efficiency and the lower cost and sustainability of growth in our industry. But what I hope you realize from the examples that I showed today is that, okay, the conventional way that we've been working in our industry, where device people just focus on miniaturizing the transistor, and that automatically improves system performance, and we have had technology roadmaps to guide, like manufacturing, equipment development and process development and so on. We've really, in the past, not really collaborated too much with like software engineers, right, for device designers. But in the future, I think what we'll need to do in order to achieve orders of magnitude improvements in performance and energy efficiency, we need to really have applications start to drive innovations, co-innovation and co-optimization of devices, circuits, and chip architectures. So I think once transistor scaling slows down or stops, co-design and innovation across all this innovation stack is going to be needed to achieve dramatic improvements to sustain Kurzweil's law. So to conclude, I hope you've seen that we have lots of alternative approaches to enhance chip performance, even beyond the end of Moore's law, to sustain this virtuous cycle of technology advancement in our field. So we can look forward to the age of ambient intelligence, where information technology will be ubiquitous, embedded, hopefully benefiting humans and society, and to ensure an equitable, healthy, sustainable future for all. Thanks very much, and I'd just also like to acknowledge my students, postdocs, collaborators, and all the companies and the facilities that made this work possible. And I look forward to engaging you in some questions. Thank you.
When you showed that array of switches with a left part and a right part, that was for me very much reminiscent of a PLA that could be programmed to do a function. How far am I from this idea?
Yeah, that's great. I think, yes, some of my students actually did propose, and other groups like at Stanford have proposed using this back-end of line reconfigurable interconnects for like programmable logic devices. And the nice thing is, like that lookup table, it's reprogrammable, right? Those switches can be reprogrammed, so it can be an adaptive lookup table, right? So a lot of applications for electronics in the future have to be adaptive, and so this is why I think reconfigurable interconnects are interesting or worthwhile to look at. Yes, but it's a good point. You're absolutely right.
Hi, very nice talk. Really enjoyed it. Rajiv Joshi from IBM. On the MEMS devices, normally in CMOS, what we do is, for reliability, we have all the testing and all that. It's well chopped out plans, right?
Yes.
In MEMS, how do you do that?
Testing?
Yes.
This is where this opportunity for the industry to develop, testing protocols and equipment. That's a good question. Well, I think there's still honestly some work needed to optimize the material. So, what we did was we formed these back-end of line interconnects, reconfigurable interconnects. We didn't optimize the contact materials. We just used, the copper and the liner. In the future, maybe the industry they already are developing, selective atomic layer deposition techniques. So we probably should coat the surfaces of those mechanical switches with something that's durable and will provide, very consistent contact resistance. So once we have very robust and, long endurance switches, then we can develop some robust test methodologies. But you're absolutely right. So this is work to be done, and it'd be great to collaborate with people in, the EDA industry to start thinking about that as a challenge. Thank you.
Thank you very much for the interesting talk. So, whenever an electrical engineer hears mechanical, there is the question of endurance, and you just mentioned endurance.
Yes.
And, there is the reconfigurable interconnect and all that, which sounds great because the number of switches there, when you reconfigure, can be kept under. But anything that works like a clock, with megahertz and higher, you really need 10 to a really large number in terms of endurance. So how do you respond to those? I mean, and
yeah.
I'm sure you've had these for decades. So, but what's the most current answer?
That's a great question, very commonly asked, actually. So my group has been, originally worked on mechanical switches for logic, for computing. So we did look at endurance challenges. So, part of it is highly dependent on the contact material. So the switches I showed here, they have tungsten as the contact material because tungsten is a refractory material. It's hard, it doesn't wear out mechanically. And what we found, we did accelerated lifetime testing, is that the voltage between the source and drain when you contact, so if you actually try to force a voltage difference between the source and a drain, even when they're in contact, then that will cause joule heating, and it can cause eventually welding, so the switch stays stuck shut. Now that's actually quite interesting, a phenomenon for implementing non-volatile switches, if you want to use mechanical switches for logic. But let's say that's undesirable. So we found that the endurance before welding will improve exponentially if you lower the contact voltage. So for tungsten, if you lower the contact voltage below 1 volt, the endurance is projected exponentially to be exceeding 1e16, 10 to the 16 switching cycles. Now 10 to the 16 is important because if you think of the like Internet of Things applications, and let's say these switches operate at 1 megahertz or 100 megahertz, but Internet of Things applications, the switching, the duty cycle is, the activity factor is not that high. Let's say 10% at the most, or 1%. And you would like to have these devices last for 10 years. Well, so let's say switching at 1 megahertz for 10 years, that's far below, like 3 times 10 to the 15 or something like that, switching cycle. So for the application, we think it's no problem. But for the reconfigurable interconnect application, if you notice, when the state of the switch is changed, there's no current flowing at all. There's no voltage difference between the data lines and the mechanical beam. So it's cold switching. So what I explained to you earlier was hot switching. If we do cold switching, I'm pretty sure that contact reliability will be fine. We just need to engineer the mechanical structure, which material scientists know how to do, to minimize the strain, or to make sure that it is well below the yield strain limit for the material. Thank you.
Thanks a lot. Those are very exciting perspectives. One thing I didn't get, you just mentioned switching frequency, for example, 1 megahertz. So what might be frequency which these mechanical switches could achieve? I didn't really get a sense of that.
Good question. So the scaling behavior of mechanical switches is fairly ideal. So if you scale down all the dimensions, and including the air gap down, you can lower the voltage and increase the operating frequency. So if you remember Dennard scaling, it actually exactly follows that, and experimental results by other researchers have shown that. So gigahertz, I'd say practically, if you're looking at nanoscale switches, probably the resonant frequency amount would be gigahertz, low gigahertz. Yeah. But for the applications that we have in mind, maybe it's not necessary. Oh, I forgot to point out, it was hopefully obvious, we don't rely on the switching speed of the mechanical beam to actually perform the function, like the lookup function, right? So that's why the readout delay can be low, because the contact resistance can be low compared to a CMOS circuit. But so I guess if you really want to do mechanical computing or the oscillators, it will be limited by the resonant frequency. And I'd say safely gigahertz, you can assume, is relatively straightforward to achieve with modern process technology. Thank you.
Hi, I've got a question that might be slightly off topic, but as a parent of someone, of 2 people that started in engineering, one's currently at Berkeley,
Well,
they got
congrats.
transported into the software world, and I see this not just with my own children, but many people having trouble getting them involved in this kind of research. And so do you see that?
Very timely question.
Yeah.
Yes. Actually, just the reason I just arrived here, because at Berkeley, our EECS department is having an industrial advisory board meeting today, and we were just talking about this topic. When I was chair of the EECS department, like many years ago, I was already telling executives in the industry, well, if you're paying software engineers so much compared to hardware engineers, I'm pretty sure you're going to see you're not going to have enough hardware engineers graduating in the future, and that's where we are today. So a study done by SEMI and Deloitte a few years ago, it was a survey of CEOs, I guess, in the semiconductor industry. Over 80% of them at that time already said that they could not fill all the technical jobs they had available. And today our federal government, our legislators are considering whether to fund the CHIPS Act, which would infuse tens of billions or hundreds of billions of dollars into the semiconductor industry to increase manufacturing activities in the US. And so there is a huge workforce development gap. You're right, because the gap already exists today, and if our government expects us to double the number of jobs and the activities in semiconductor manufacturing for economic competitiveness and national security, we are in trouble. And so I've been part of a group of faculty who've been trying to advocate to establish a nationwide network of universities and colleges to revitalize the semiconductor curriculum. We work together with industry to make sure that the content of our courses is updated, that it's attractive to students, because you're right, part of the challenge is, Okay, like we don't have up-to-date courses at many universities, so we can't train them as many as are needed. Also, the students are not attracted to our field. So I don't know how many of you have seen, I just saw last week a nice video made by Semi, sort of talking about our field. Like there's like, I think it's like 3 or 4 young, attractive people who are engineers, like working together to like solve a pandemic problem, right? And so it's like a movie, like a preview for a movie. And that something like that, working with media to really get the message out that this is an exciting field, rewarding careers, making a positive impact on society, right? Helping to solve the global climate change issues, the pandemic, other natural and man-made disasters. I think if we get the message out, a lot of the students, not all of them, some will always be attracted to just money and so on, but others, actually, if you interview students, engineering students especially today, the majority of them do care about the future, like of the world, sustainability, equality, or equity, and they would be attracted as long as they know that they're making a positive impact in their future, helping to shape a better future for all. So I think it's a matter of collaborating with industry to make sure our curriculum is up to date, helping to attract students from maybe a greater diversity of schools across the country. In this country, we actually have a diversity of talent that's untapped. The National Science Foundation calls it the missing millions, right? So we have a lot of women, students from underrepresented groups that maybe don't realize that engineering could be a rewarding career for them. And so, we should be working together with a diversity of universities, not just Stanford, Berkeley, MIT. It really should be R1, R2 universities, minority-serving universities, community colleges, because we know a lot of the needs in the manufacturing, facilities are for technicians, and they just need community college. So this American Semiconductor Academy initiative is something I've been pushing. We have dozens of companies that have provided letters of endorsement. We're getting the message out to Congress at this point. It's the House of Representatives is working on some bills, their version of the bill to fund the CHIPS Act, sort of trying to get our message. We've been working to get our message and to people in the Department of Commerce, because a lot of the funding would be appropriated through the Department of Commerce to companies and for workforce training. So I'm actively working on that to get that message to Secretary of Commerce Raimondo, and I think most of the semiconductor company CEOs now are aware of this initiative, and they're all very supportive of it, because if we don't, so $50 billion invested by the federal government. The Semiconductor Industry Association, in a report published this May, mentioned that they expect this to yield over 40,000 new semiconductor manufacturing jobs in the next 5 years. So that's like average of over 8,000 new jobs per year created. And today we can't even fill the jobs that exist. And then there are going to be more jobs like in design and so on and so forth, and software. Like, how are we going to fill that need? If our federal government invests this money and companies come and like Intel and TSMC build fabs, but they can't fill them, they're going to have to be forced to build fabs elsewhere. And that's not good for our country in the long term. So this is why we're pushing really hard. If the government's going to fund the CHIPS Act, they should really appropriate funding to set up a university network. And the thing is, universities, engineering is all about teamwork, collaboration. I strongly believe that we need to sort of follow our own, what our teaching, right? We need to collaborate. Faculty at universities around the country need to collaborate. We need to help each other update our curriculum. So let's say at Berkeley, for example, we have really good courses in EDA. I'm not sure, actually. But we can package that up and enable any faculty member in the network who is interested to be able to create an EDA course quickly, high quality, to train their students. Because the need is so great. No single university is going to be able to graduate 8,000 new graduates a year, right? We need all the universities that are interested and colleges to contribute. And so we need to empower the faculty across the country to be able to teach, modern curriculum to attract and retain students to supply them to the semiconductor industry. So it's time for us to start something like that network. So I've been, advocating for that. And if anybody's interested, I'd be happy to share with you some materials and a draft letter of endorsement to really just show people, legislators and leaders in Department of Commerce, Department of Energy, Department of Defense, that this is something that And NSF I've already talked with. They're interested, but they're going to start a new technology directorate, so they're going to be working internally to solve things. So it might take them some years to set up a program. We really need like hundreds of millions of dollars per year to attract and retain students to study. So a lot of that money is for scholarships, fellowships, and to pay for internships, so students don't get attracted to software. Right? So much of that
Thank you.
funding, yeah.
It sounds like you've been working hard at this.
Yes, we are working hard on that, but thank you. All right, I guess that ended.
Any other final question?
Great.
It's hard to follow on such a far-reaching discussion on topics that go well beyond design automation in engineering.
But design automation is key, right? We want to, actually, Synopsys, Cadence, Silvaco, we'd like to make these tools available to students at all these universities and colleges so that they get trained to, use them.
Yeah, so my question is really about design automation, and we've had at DAC for many years, we've had companies that do, for instance, MEMS design, like Coventor and all that. I'd like your opinion on the state of the tools and the state of the design automation in an area that is slightly sort of beyond what normally logic and analog design goes and these emerging devices.
Yeah, I think the EDA tools, okay, so first of all, let's say compact models used for EDA tools there's a field of research now, which is great, applying machine learning to more quickly arrive at optimized, parameters for compact models. That's great. But TCAD tools definitely have advanced. So the oscillation, I didn't show that, but we've actually used Coventor, Coventorware to simulate our oscillating relays, and they actually do mimic what we measure experimentally. And we've been using the simulations first to verify that if we have an array of oscillators and they're coupled in different ways, that the oscillators will settle into different phase configurations, right? So we've done that all by simulation. So I think the simulation tools are very sophisticated and have evolved with technology advancements. So definitely we are still relying on those for the most innovative new device concepts. Yeah. Okay, thank you so much. Good questions.
Thank you very much.